Okay, here we go. Day 2, and it's going to be a good one. So you should have your notes packet, that bright yellow notes packet. We finished up with Power Series yesterday, and today we're going to look at starting Taylor Series. Dun dun dun. And we're going to look at Taylor polynomials, and I've been talking about these forever and telling you how these are really cool things that we can use to approximate other functions. So at this point, everybody, I hope you have your notes ready to go, and we're going to look at the first thing. Says Taylor polynomials can be used to approximate other functions such as sine, e to the x, and ln x. We have done this before. I mentioned this before. When we have the function sine x, if we want to approximate it at x equals 0, we have used tangent lines before. And now nobody can tell me you don't know what a tangent line is. Let's think back. We've used tangent lines to approximate functions. How do we do that? Well, we need a point and we need a slope. How many times have we said that? And so the point comes from the original function. So if we're at x equals 0, the sine of 0 would be y, or f of x also equals 0. Okay, cool. How do we get our slope? Well, you remember we take the derivative, and the derivative of sine is cosine. And then if we take and plug 0 into our derivative, I do believe we're going to get a 1, and that represents our slope. And then we would write it in point slope form. So this would be what? Y, the point is 0, so y minus 0, I'll just write it out like that, equals the slope 1 times x minus 0. And then remember when I said if we brought this constant over to the other side and we wrote it y equals 0 plus 1x minus 0, this would be a Taylor polynomial to the first degree, because this is to the first degree right here. And we've done this before. Now this turns into y equals x, right? Nothing too very exciting. So if we want to predict the sine of x at point 2, which is what the problem is asking us to do here, that's going to be the same thing as y, right? Y equals x, so it's going to be approximately 0.2. And then we've been asked questions like, is your estimate an overestimate or an underestimate? And hopefully you remember how to figure that out. Yes, that's right. Everybody's saying check the concavity. And that would be the second derivative, which the derivative of cosine would be negative sine. And this is going to be negative at 0.2, right? Sine would be negative at 0.2. So f double prime at 0.2 would be less than 0. So f is concave down. And therefore, this would be an overestimate. Remember, a concave down thing looks like this, and if we put a tangent line on it, it's going to be above it, and therefore an overestimate. So all along, I think I mentioned this back way in the beginning of the year, that if we write it like this is actually a first degree Taylor polynomial, and it does in fact predict what the sine function is around 0.2, because remember we have to be close to 0, because that's what we know about. We know something about 0. If you were to get your sneaky calculators out and you were to put this in your calculator, you would in fact get, whoops, oh Lord, can't erase this fast, 0.198669. So 0.2 is pretty darn close to what your calculator value would tell you. So when we do this first degree Taylor polynomial, we write the function at whatever value we're trying to find plus the derivative of the function at that value times x minus that value. Kind of looks like x minus the center, perhaps. Have we seen that in other things lately? I think so. Now, this is but a first degree Taylor polynomial. All linear equations are. If we were to make higher degree polynomials, we would have better and better predictions of our functions close to the center. So our predictions are always good if we're close to our center. So that leads us to our box of fun stuff, which would be on your, whoops. Okay, what just happened? Sorry. Let me slide this in here. So here's our box of fun stuff, and we have these pictures of these two cool guys. Guess what? One of them's name is Taylor, and one of them's name is Maclaurin, and hence the name for Taylor polynomials. And if you look at this, we want to write a polynomial centered at x equals c. So look right here, that's what I was just showing us. That's a first degree. And then look at this fancy thing right here. Well, what does that mean? Take the second derivative at our value c and divide it by 2 factorial. Wait, what? And then look at x minus the center squared, and then plus dot dot dot. This is the number of derivatives right here, and over that number factorial at whatever c value, x minus c. Now I know this looks kind of funky, but we're going to get good at this. This is called the nth degree Taylor polynomial. And this, your center could be anything for this format right here. So note to self, a first degree Taylor polynomial is a tangent line at whatever value you're looking at. Second note to self is this business right here about the derivative and the factorial, when you plug in your c value, that represents the coefficient, okay, or slope, because it comes from a derivative, right? And it goes in front of the x minus the center to the end term. And so definition of a Maclaurin polynomial is the same thing as a Taylor polynomial, only it is centered at c equals 0. It's always 0 for Maclaurin. So if ever in the instructions that say write a Maclaurin polynomial, your center is 0. And this is our nth degree term. So this is just a pattern that happens over and over and over, and centered at 0, so we don't have x minus the center in there. And again, if the question says write a Maclaurin polynomial, then you know you're going to do that and center it at 0. Highly exciting stuff, I know. So our next goal here is to find a Maclaurin. So we're looking at example 3. Did we already? Example 1, do we not have an example 2? Well, all right, that makes our life a little easier. So we're on example 3. Numbers, they don't have to go in order. And this one says find a Maclaurin polynomial, degree n equals 7, so that's 7th degree, for sine x. Use the polynomial sub 7 to approximate the value of the sine of 0.1. And then use correct notation, find the error for your approximation. Oh, all these fun things. All right, well, let's see. How do we do this? Well, if we need a 7th degree Taylor polynomial, we got to start with f of x equals sine. Okay, and we're doing this at x equals 0. So we're going to plug in 0 to the sine function. If we plug a 0 in the sine function, we get out 0. This is going to be our list of coefficients right here. Then we take a derivative, okay? And the derivative of sine is cosine. We plug in 0 to the derivative. That's like our c value in the formula, and we get out a 1. Wonderful. How long can we do this? This is going to go on for days. Here we go. Derivative of derivative of cosine is negative sine. Let's plug 0 into negative sine. Don't we get a 0? Let's see somewhat of a pattern going on here. So now we're going to do our third derivative. Derivative of negative sine is going to be negative cosine. Put a 0 in here, and we're getting negative 1. And I think some of you can predict the pattern going on here. This turns into a 4 now after we make our 3 slashies. And the derivative of negative cosine is sine. That's going to be 0. If we kept going, let's just do this because we're having so much fun. Derivative of sine is cosine. And if we put a 0 in there, we're going to get 1. Oh gosh, I could do this all day. How about you guys? Whew, negative sine. We're going to get 0, and then f of 7, seventh derivative, sorry, not f of 7. The 7th derivative is negative cosine. Oh my goodness, that was a lot, huh? Okay, well, we need these as our coefficients, and then we're going to put them into the pattern that we looked at in our box of fun stuff. So I know you're all dying. What are we going to do here? Well, here's how the pattern is going to work. This is our first coefficient where it's x to the 0. So I'm going to write it out with this. So I'd have 0 plus these right here. Then I'm going to have x, and instead of minus 0, I'm not going to write that. It's x to the first, right? Well, this coefficient is a 1, and I'm going to put all of this over 1 factorial. Whew, it's very exciting stuff. And then plus, I would do 0, and this would be an x squared. My coefficient is 0, and this is going over 2 factorial. I know, you're all thinking, that's a 0 there. Why are we doing this? Well, I'm showing you the pattern. And so, whoops, just when I thought I had it. Negative 1 is our next coefficient, so minus 1. This is going to be x cubed, agreed, over 3 factorial. Whew, all right, let's keep going. And then plus 0, x to the 4th, you guessed it, over 4 factorial, plus, this next one's a 1, x to the 5th, over 5 factorial. What do we got? Plus 0, x to the 6th over 6 factorial. And finally, minus 1 over 7 factorial, x to the 7. Whew, that is how we're going to write our polynomial. And now we can let these things go that have zeros in them. So here's what we're trying to do. We're trying to write out a Taylor polynomial, or this one's Maclaurin, right? Because we're centered at 0. It's approximately, now we're going to use this notation, p sub 7, because we were told to do a 7th degree. And now what's left over in all these terms? Because a lot of them are 0. So isn't the first term going to be just x? That one goes. This one's going to be minus 1 over 3 factorial x cubed. Let that one go. This one's going to be plus 1 over 5 factorial x to the 5th. And then minus 1 over 7 factorial x to the 7th. Whew. And we have, in fact, written up our first Taylor polynomial. This represents the sine function. Kind of cool. And if we want to predict the sine of 0.1, well, what does that mean? It means I would take my 7th degree polynomial that I've created here, and I'd replace those x's with a 0.1. And I'm going to cheat in order of time here, and I'm going to tell you what that is. 0.0998. Which, if you put this in a calculator, I think you're going to get just about the same thing. So this approximation was pretty darn good with those 4 terms. Now remember, this polynomial could go on, right? And we could make this higher and higher degree. But isn't that kind of cool? How you can predict the sine function at 0.1, which is this amount to 4 decimal places. And I think that's pretty much what a calculator would tell you. So powerful, powerful stuff here. Shall we try one more? You think we can do it? So let me just recap. In order to get our coefficients for a 7th degree polynomial, we needed 7 derivatives. Now I bet a lot of you could see that after the first 4 here, it started repeating. So we probably could have predicted what these were going to be. But we're such good students, we're going to remember this pattern right here for sine. It's one we're going to commit to our memory, and we'll be good to go with that because we need to know sine and how to make this. And this pattern will always hold true for the sine polynomial. Which leads me to example, does this one say 4? Oh good, this goes in order. Okay. What does this one say? List the first 4 non-zero terms and the nth term for the Maclaurin series. Oh, well, I think we kind of just did this, but let's see. We need the first 4 non-zero terms for the sign. So I'm just going to write this out again. I guess I'm just going to write the 4 terms. Yada, yada, yada. Here we go. Wasn't it x? And then was it minus x cubed over 3 factorial? And then plus x to the 5th over 5 factorial? And then minus x to the 7th over 7 factorial? So, and then we're going to do plus dot, 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 3 dots, 3 dots. And then we need an nth term. It's alternating, so we're going to give me a -1. Should we try that to the n and see what happens? And then it appears we have an x to something here. Well, this is 1, 3, 5, 7. Let's think about starting this on 0. If n equals 0, would that work here? I think it would. If we plugged in n equals 0, that's going to be positive. Okay, and if this was to the 0, okay, wait, it can't just be n, can it? I'm thinking it's going to be 2n plus 1. All right, let's think about that. Just for the x's, if we plug a 0 in, do we get x? And then if we plug a 1 in, do we get x cubed? And we plug a 2 in, we get x to the 5th. We plug, perfect. And now, isn't it true that this exponent matches this factorial down here? So couldn't we say 2n plus 1 to the, not to the, 2n plus 1 factorial? Excellent. Plus dot, dot, dot. And this one I started on 0. Remember, hopefully you can see all that. Remember the other way we could write this is with our summation, and we can say n equals 0 to infinity. And we'd put our -1 to the n, x to the 2n plus 1 over 2n plus 1. Hey, just a little sidebar here. If you watched the videos from yesterday, there was a mistake on example 8. Some of you caught that mistake. I think I put 2n minus 1 here when it should have been plus 1. Just wanted to put that out there one time. I did send a text to say that that happened, and I did put a little note on the e-class page, but just wanted to add that in. There is a mistake on example 8 in the video. So anyway, for now, this is going to be my, I'm going to stop here, and I'm going to pick up with another video shortly. So there will be another one to watch, but I will stop this one here. Hope you're enjoying this as much as I am. Ta!